Good afternoon, everyone. My name is Josh Bergen. 2 years ago, I had the opportunity to come and speak here, and I'm flattered to have been invited back a second time, so thank you. My background includes high-tolerance mechanical applications. I founded Precision Machinery over 10 years ago, and one of the things I try to do is be personally involved in as many installations and projects as possible. That has allowed me to learn from men and women such as yourselves in over 200 mills across North America, Australia, and New Zealand. It has been a privilege. Precision is located in Western Canada, and we have a large presence across North America. We work with Chematic Technologies here in Australasia. While we provide other manufacturing services and equipment, saw guides and their maintenance has been a primary focus for us over the years. In addition to saw guides, Precision manufactures molds, manifold alignment systems, CNC guide dressers. Our popular semi-automated version is operating in over 115 mills now, and lubrication systems. In the last 2 years, we released our new Kaiser equipment line, which includes a fully automated version of our popular CNC guide dresser, a fully automated disposable knife grinder, and a fully automated Babbitt molding machine. As a company, we have always been focused on one of the most critical components to the manufacture of lumber, the saw guide. The time, cost, and careful work you put into your saws is devalued without properly manufactured and maintained guides to support them. As I once heard it put, a saw guide is the micrometer of your mill. I go into countless mills that are measuring lumber to thousandths of an inch, but then ignore the very component primarily responsible for sizing and deviation. When I was here 2 years ago, I talked to you about guide maintenance and our new Teardrop pads. If you weren't here for that or don't remember, I'll give you a quick recap. This revolves around lubrication and support of the saw during operation. I will be talking about this more tomorrow in the afternoon workshop. The cooling and lubrication of a saw is commonly done with Babbitt pads mounted to a steel or aluminum saw guide. Historical conventional pad design theory involves a machined surface called a land around the pocket of a Babbitt pad. During operation, lubricant, usually a mixture of water, oil, and air, is pumped through internal galleries into the pocket. The pocket fills and lubricant is forced out onto the guide lands. The saw runs on a film of lubricant radiating outward from the filled pocket, essentially creating a flat bearing. That theory is out of date. In Western Canada, we have a scientific research organization called FP Innovations. They are not-for-profit, funded by industry, and their mandate is to further innovation and development in the forest sector. In 2016, we wanted to know if the industry's conventional lubricant supply theory was accurate. We found it was not. For simplicity, think of the rotating saw acting like a pump. The movement of that saw, or pumping action, wants to draw fluid from the reservoir or pocket of the Babbitt pad. Depending on the direction of rotation and the shape of the pad, only certain areas of the support land receive proper lubrication, limiting the effective support and cooling area. In addition, the pocket experiences only a partial fill. The question then was, is there a better pocket or pad design? Several gallery and pocket designs were tested. The design that was eventually settled upon was what we refer to as a teardrop. You will hear me refer to the teardrop shape of the entry port. I am referring to these parts of the guide pad here and here. Here's a close-up to give you a better visual. Rather than supplying lubricant to a pocket, we direct flow to the top of carefully designed guide lands, feeding them directly. In this drawing, you can see there is an entry land, but no exit land. We'll review that in a moment. Here's a recap of the test data from 2016. A set of saws was ganged up with conventionally designed guides and pads. Temperature sensors were put on the saws. The saws were started and several cants ran through. It took an average of 80 seconds for the saws to cool back to their pre-cut temperature after cutting. When the saws were run with the teardrop design, the cooling time dropped to 7.5 seconds. It's fine if saw temperature increases uniformly during cutting, and we don't wait 80 seconds between cants. What the test showed was the extreme improvement in lubricant delivery to the saw. With tighter environmental regulations and increased cost of lubricants, being able to reduce usage and prevent saw damage is critical. Please contact us if you want to have a copy of the full report. I love new ideas and I love innovation, but I also believe in real-world proof. We performed the first teardrop conversion in North America and we have permission to share this information. There is a large West Fraser mill nearby our facility. The mill asked us to redesign and update their gang to the teardrop system. Before the conversion, the mill was changing saws once per shift. After conversion to the teardrop, the mill went to one saw change every 4 shifts. They were so happy with the results they converted the rest of their remaining machines. Since that initial conversion 3 years ago, we have over 60 mills now using our teardrop system. You can see a few of the before and after overlays here. The intent of the teardrop design was to achieve the same saw cooling with less oil and water into the saw box. What we have seen in a majority of our conversions is a substantial reduction in guide wear and saw damage. That translates to reduced deviation, longer run times, and less work to the saws after a run. While a handful have not experienced those gains, they have been able to reduce oil and water. So, the teardrop design has not only proven out scientifically in a test environment, but it has proven out in real-world application with resounding success. I want to briefly mention the entry and exit lands I noted earlier. Initially, the scientists at FP Innovations felt the top and bottom lands may not be required. That was because the testing showed the lands added friction, as lubricant and support was happening on the curved guide lands. We have always maintained that the entry land must stay in place. We don't want to leave a larger opening than necessary for small debris such as slivers or sawdust to get caught. The small 1.5 thou gap for standard saw clearance is preferable to prevent this. Further testing showed a trade-off between heat and support. While the exit land is another friction point, it performs a couple other important tasks. The first is support. While it may add some heat back into the saw, it slows pad wear in the area. The second more important benefit is that it allows pressurization of the pocket. Let me explain. In historical lubrication systems, air, oil, and water are used in combination. You can see a picture of a couple of the lubrication systems we have here on the screen. I was always told that air was a mixing tool, agitating the water and oil together, but air actually does a lot more. Consider orifice flow. If you drill a 3/32 hole in the bottom of a bucket, that hole will pass 0.21 gallons of water every minute at atmospheric pressure. I use the 3/32 number as that is a common hole size defined in saw guide lubrication ports. If we consider an average teardrop guide, there are 4 orifices per saw. Now many saws have more than this, but let's consider the 4. So, drill 4 holes in the bottom of my bucket, and we are now passing 0.84 gallons per minute for each saw in our system. A 10 saw system then would be the equivalent of 8.4 gallons per minute or over 30 liters per minute of flow. Now I realize this is a very basic calculation, it is not a proper flow calculation. Calculating flow rate in such a system is very complex as you have to consider pipes, sizes, pressures, volumes, etc. The point is that the water required to properly fill and supply such a system is substantial. Now introduce air. If you put oil through a clear line and then introduce air, an interesting thing happens. The oil flows around the outside of the pipe while the air passes through the center. Air becomes a carrier. Air provides volume and pressure and allows us to equalize flow through the guide system, especially in larger machines. Air also provides pressurization of the guide pocket, creating an air seal against foreign contaminants in the pad. Such air seals are common on bearings in many applications. That's why you will see these reliefs in our guide pad design. It allows air to positively pressurize the pocket area. When developing such things as new pad design, to be scientific we must gather data or measure something. For me to simply tell you a saw ran longer means very little. I'm sure we've all seen saws run from mere seconds to weeks. So much is dependent on other factors that we can't see in the saw box during operation. In mechanical applications we often measure temperature. Vehicles have many rotating components that are monitored for heat, even in your mill, gearboxes, planers, etc. The list is extensive. FP Innovation just realized this and came up with a rudimentary temperature sensing system they would use in the lab and field during testing. You can see a picture of that original system depicted here. This was a bolt-on box that had spring-loaded sensors contacting the saw. I have a couple of good friends that are saw filers. One thing they do not like is anything touching their saws. That includes people. Springboarding off of FP Innovation's initial contact temperature sensors, we started development of a non-contact version of a sensor. What you see here in the picture is that non-contact sensor. This was one of our initial test mills. We elected to go with a single sensor near the rim of the saw where we were most likely to see increases in heat. To date, we have provided the mill with customized guides from our guide factory, but we can modify most existing guides to house these sensors. We also have alternate mounting options and configurations. Here is a dual integrated sensor, a dual bolt-on sensor mount, a rail mount sensor system. I could go on, but the point is, as you can see, the system is highly customizable, simple, and contained. Some mills want to be able to see the difference in temperature between the rim and eye, so they can analyze if there's an inconsistent heat change across the saw. While that data is interesting, I feel it hasn't led to greater gains in predictive analysis. We have found the single integrated sensor to be the most effective version to date, as it gives us solid information on saw performance. Oftentimes, we have to determine what data is important. When there is an increase in the differential between eye and rim, it always happens during an incident that raises saw temperature. I like to look for changes from normal. A good operator knows how his machine should run during normal operation. Often he even knows if it sounds wrong. We watch for those spikes in temperature that indicate an issue. The software allows you to set alarms for yellow warn and red alert. Once these settings are established, your staff can start to predict potential problems and failure. Rather than reacting to a problem, such as off-size lumber, we can see when a failure may occur. As familiarity with your particular machine develops, you have options to tie temperature warnings into your control system. For example, if a zone starts to heat up, you may choose to raise water to that area in order to run to a more appropriate time to shut down and change saws. You may also elect to reduce feed speeds or gap for a brief time in order to keep the saws cooler. You may even choose to perform a saw change rather than experience a failure. Let's look at how we get the sensors into the guide stack. Rather than mounting sensors in every individual guide, we monitor the saw in zones. We can mount the sensors in every guide, but again, I come back to what data is necessary. As example, take this vertical single arbor machine with 14 saws on the arbor. We mount 3 sensors in the stack, one in the primary cut zone at the base of the stack, one near the top end of the stack, and one in the middle. That's 3 sensors across the saw set. We can change this to any configuration and increase or decrease sensors, but this gives us an excellent idea of how the stack is performing. The sensor itself is small. It transmits data wirelessly, so there are no wires to connect to the guide. The batteries in the sensor are guaranteed to last 1 year. You can enable or disable a sensor and see its data using an app on your Android phone. We have options for cloud-based or local monitoring. It's important your maintenance staff can see what's happening with temperature in real time. We like to set up monitors in the operator's booth and saw shop. This allows staff to build familiarity with normal and abnormal temperatures. One final real-world example, because they appeal to my practical brain. We had a vertical double arbor running 14 saws per arbor. We were able to reduce water by 7 gallons per minute across 4 zones without increasing saw temperature. That's 420 gallons per hour and 4,200 gallons in a 10-hour shift. This particular mill ran 2 shifts, so that was a total reduction of over 8,000 gallons of contaminated water per day that is no longer being run through that one machine. Environmental gains are not our only benefits. We have to deal with sub-zero temperature in our area, and for that reason alone, the mill was very pleased. Additional benefits were for secondary uses for the byproducts of lumber production. For example, the sawdust was drier. Another of our mills used the temperature feedback to optimize feed rates on larger diameter wood. They found that when they ran too many large cans in a row, temperatures would spike and cause damage to the saws. By increasing gap slightly, the mill was able to run longer between changes and increase production. One mill, running multiple arbors, found one of their zones was 12 to 15 degrees hotter than the others. When they investigated, they found a cracked supply line. As always, I appreciate the opportunity and I hope I've prompted some discussion. Thank you for your time.